Hi guys, welcome to a new chapter, Functions and Relations. And you'd be familiar with coordinates and set of values. We've done that in straight line graphs and parabolas, and a few other different types of graphs. But relationships is very much corresponding to coordinates and the sets of values and data that it provides. So basically, I've got the four types of relations here, which will give which illustrates the different types, and hopefully these diagrams helps understand what relations are. Okay, and we've got four different functions. First one, straight line graph, is I guess the best example of a one-to-one relation. So for every x value, there is one corresponding y value. Okay, so if we talk about coordinates, there's only one set of coordinates, one x and one y value that provides that set of data. One-to-many is that for every x value, you have multiple y values or more than one y value. We have kind of like a sideways parabola here. And so you could see that the vertical dotted line, which represents the x value, that is producing two possible y values that corresponds with that. So one-to-many, one x value has more than one y corresponding value. On the flip of that, you could have many x values that corresponds to one y value, and that is many to one. Okay, and then that's an example of a parabola, and we've done that a few times with our quadratic functions and working out solutions for x in parabolas. Sometimes some parabolas, depending where they're placed, will provide no solutions, one solution, or many solutions. So in this case here, a parabola is a perfect example for many-to-one relation. And then lastly, many-to-many is when you have more than one y value for every x value, and also you have many x values for one y value. So it works both ways, and a perfect example for that is a circle. You could see that regardless wherever the point of the circle that you're at, you have multiple or more than one corresponding option, depending whether you are, I guess, referring to x or to y value. Now, what's interesting about these four types of relations is that two of them are actually functions, okay? And so I'm going to highlight those that are functions, which is one-to-one and many-to-one. And that's why we've probably spent a lot of time on straight line graphs and parabolas, because they are both functions. And what makes separates these two relations compared to the other two is that there is only one y value for however many x values there are. Okay, so relations that are one-to-one or many-to-one are called functions. And so a function is a relation where there's for any x value, there's only one y value that corresponds. So here we have two relations which are functions. And a perfect way to test it out if they are a function is the vertical line test. So every time that you cut through the function vertically, there's only one intersection point available. So here we'll do a vertical line test as well, and it only cuts through the function once. Whereas if we were to do the same thing to the others, you'll see that it'll always cut through more than one point. Therefore, it's not a function. If we did this with a circle, it's cutting through the graph, more than once. So they are not functions. These guys are not functions. These are. Now, for a while, we've been used to saying y equals mx plus c, or y is equal to ax squared plus bx plus c, and everything is just y is equal to whatever it is. But because these are functions, we could also replace it with f of x. And we've done this a little bit with polynomials, where you will need to substitute a certain value. And basically, we're saying that y is a function of x. And whatever's set in the brackets, for example, if we had the function of x is equal to 2x, okay, and then we want to know what the function of 2 is, basically we're going to be replacing x with 2. So 2 times 2 is equal to 4. Similarly, if we had, say, f of x is equal to 3x squared plus 4x minus 7, and we had f of 1, we're going to be replacing x with 1. So 3 times 1 squared plus 4 times 1 minus 7. So 3 plus 4, 7, minus 7 is 0. So f of 1 is equal to 0. Okay, so then in this case, f of 2 is equal to 4. Now, the next thing I want to cover is the terms domain and range. So domain and range. And I don't want you to get these two mixed up. The domain is basically the set of values for x, okay? So the domain of a function is the set of all values of x for that particular function. The range is going to be the opposite, okay? So it's going to be a set of all values of y. Now, for something like a straight line graph, we could see that these arrows indicate that it's just going to infinity, and this is going to the other direction as well. Okay, so we can say that the domain is basically all the real numbers of x, okay? And for the range, it's also all the real numbers for y. There's no limit to what the values are because it continues on, okay? But for something like this case here, which I'm going to draw on the right side, well, it's not very good, but let's just, we've got this graph here, which is just an example of f of x is equal to 1 over x, which is an example of a hyperbola. We could see that all the real numbers, it's going all the way to negative infinity, positive infinity for both domain and the range. However, it will never reach 0. Okay, it doesn't hit 0. So they're the values, I guess, that is excluded. What we can do is then we write that the domain is all the x values, all the real numbers, but it excludes, okay, so it excludes 0. The same thing with the range, all the y values going up and down, they're all the real numbers, all possible numbers, but because it doesn't hit 0, we are going to exclude 0 from the range. And so what you're stating with domain and the range are all the possible x values and all the possible y values. You can restrict the domain and the range on how you graph it, depending on certain limitations, and we'll see this throughout the chapter. We can identify other features of functions by substituting values and seeing where, I guess, the the y value or the function value, what happens to that when you substitute x for certain numbers. So, for example, if we had the function f of x is equal to x squared, we're familiar with that being a parabola. Let's say if we substituted f of x as f of 10,000, okay, we'll end up getting, say, 1 billion, okay? So 1 times 10 to the power of 9. And then if we say, I guess, put in the function of 1 million, and so replacing x with 1 million, you'll end up getting 1 times 10 to the power of 12. And so what we could say and conclude from this, that as x, or as our values of x increases or gets bigger towards infinity, that the function of f of x, which is x squared in this case, also increases. Okay, basically it also heads towards infinity. So you could kind of state that as a statement. If we tried, for example, f of x, which is to the power of minus x, and do exactly the same thing, so we're going to replace x with 10,000, we'll end up getting something like, we'll get something that is very close to 0. Same thing, if we replace it with a million, we're going to get something that's very close to 0. So what we could say is that the function, as x approaches infinity, as the numbers get larger, the function of f of x, in this case is 2 to the power of minus x, it approaches 0. Okay. Maybe a third example, if we had something of f of x is equal to 1 over x plus 1, and we did exactly the same thing and substituted x for 10,000, you'll end up getting a value very close to 1. And then if we replaced it with a million, we'll end up getting something even closer. So we could see that it's approaching 1. It's not really hitting 1 at all, but it's getting very, very close to that. So we could also say that as x increases towards infinity, that the function also approaches 1. Okay, so that's just some descriptives in terms of features of the functions. When you substitute values, you get a gist of what's actually happening. Now, something that we've done in the past when looking at, I guess, points of intersection between two straight line graphs. So if we had two straight line graphs, one's say negative, one's positive, there's a point that they cross over. Or let's say if we had a parabola and a straight line graph, there would be a point or 2 points of intersection perhaps there. Or if we had a circle and again another straight line graph, there would be 2 points of intersection. Now the thing is with these, that you'd want to I guess use simultaneous equations to actually solve for the points of intersection. So just recapping over what we've done with these 3 chapters, to work out points of intersection, you simultaneously solve those equations by equating them to each other, and you solve for x, which is your x values of those points of intersection, resubstitute them into the equation to work out what your y values are. So it doesn't matter what the functions are, you'll do exactly the same thing. Okay, so for example, here we have f of x is equal to 2x plus 1, straight line graph. And then we have another function, okay, and we're going to call this g of x. doesn't really matter, f, g, or whatever it is. And we have hyperbola, all right? And so we're wanting to see at what points do these two graphs actually intersect with each other. So what we'll need to do is equate them to each other. So 2x plus 1 is equal to 1 over x. And then we're going to be solving for x, okay? So what we'll do is we'll multiply both sides by x to get 2x squared plus x is equal to 1. Then we will take 1 across to the other side to get ourselves a quadratic expression. From here, we're going to, I guess, factorize and solve. So let's say this is a non-monic expression. So 2 times minus 1 is minus 2. That's our a times c. Factors of minus 2 that add up to 1 is positive 2 and minus 1. So we'll have 2x squared plus 2x minus x minus 1. And we're going to factorize by grouping. So 2x, x plus 1, and then minus x, x plus, oh, hold on here, minus 1, x plus 1. And then so 2x minus 1 is our first set of brackets, x plus 1 is our second set of brackets. Our solutions for x is a half and negative 1. Okay, so once we've got those two, we're going to substitute them into the equation. And so we'll have f of, say, a half is equal to 2 times a half plus 1, which is 1 plus 1 is equal to 2. And then if we did the same thing with, say, with negative 1, and it doesn't really matter if you're going to substitute into this one or this one, it's going to get the same results, okay? So f of minus 1 is 2 times minus 1 plus 1. So minus 2 plus 1 is equal to minus 1. So what we'll have is our points of intersection are, so points of intersection without even having to draw up the graph are going to be a half and 2 and minus 1 and minus 1. Lastly, I want to talk about inverse functions. Inverse graph is created when a graph is reflected in the line y equals x by about the 45-degree line. Okay, so for example, we have, I guess this is your 45-degree line, which is represented as y equals x. So for example, 1 and 1, 2 and 2, 3 and 3, etc. So that's our mirror line, okay? Now, if we had, say, the function of, let's say, 2x, okay? So what we want to do is we want to do the inverse function. The inverse function is when you actually swap your x and y's around. So x is equal to 2y. And then what you want to do is make y the subject. So y is then equal to x over 2. The other option is that it's y is equal to half of x. All right. Now this is different to when we were in straight line graphs, where you'd want to find an equation that's perpendicular to the original. Then you would have the negative inverse. We're not talking about anything that's perpendicular. We're just wanting the inverse function, and all you need to do is swap x and y variables around and rephrase your function. Okay, so what we have is we have now f of x, our original function, which is 2x, and the inverse function, so f minus 1 of x is equal to half of x, okay? And so I guess just to connect to what it used to be, we would have something like that. And if you were to graph those two lines, we would have something like this. Okay, so what we have is that f of x of 2x is represented in the green, and the inverse function is represented in the orange. Okay, and you could see how the inverse is a reflection of the original function about the 45 degree line, which is represented by y equals x. So now the thing about this is that not all functions have inverse functions that are functions. Okay, so remember that a function is I guess a graph that has one-to-one or many-to-one results. Okay, relations. So remember our vertical test. So every time that we're going through, there's always one set of solutions for y for each of those things, and that's the same thing with our original function. Okay, so it doesn't matter where you are, but so that means that the inverse function of y equals 2x is still a function, but not all function has inverses that are functions. And I'll show you an example of this, what I'm trying to communicate, because otherwise these words can sound a bit of a tongue twister. So here we have is a parabola, okay, of y equals x squared, which is represented in the green. And so what we could say that function f of x is equal to x squared. The inverse, okay, once you switch things around, will end up being plus or minus x, the square root of x. So again, if we were to switch this around, so y equals x squared, so we end up having x is equal to y squared, but we want to solve, keep things into x form, so square root of both sides, you'll end up getting y is equal to plus or minus the square root of x, because there's two solutions, all right? If you look at that graph, which is the inverse is represented in the yellow, you could see that there are multiple points of intersection. Okay, that's the first thing that we can see. But the other thing also, when we're talking about the function test, so if we were to use our vertical line testing here, we can see that if we do that, there are more than one solutions that the vertical line cuts through the graph, the inverse function. Or no, sorry, the inverse. It's not a function because it has more than one y solution when you apply the vertical test. It's just the inverse of the original function. Okay, so the point that I'm making here, not all functions have inverses that are functions. Just too many words saying functions, but hopefully that makes sense. And a really good way to actually test or predict if a function won't have an inverse function, okay, it will have the inverse, but what you'll need to do is a horizontal test, okay? Obviously, the vertical test justifies whether it's a function or not, but what you could do is you can do a horizontal test with the original function, and if it cuts through more than more than once, obviously it's not the inverse of that function is not going to be a function, okay, because there's more than one corresponding solution. So now the only way for us to be able to, I guess, make the original function have an inverse that is also a function is to restrict, put in place some restrictions of the domain. Remember, the domain is our x values in regards to how it's graphed, and then therefore when you apply the inverse, it's not going to cause the same issues. I'm going to apply that, what I've just explained, into this example here, because again, putting a visual explanation will help understand what I'm trying to explain. So back to our original quadratic function here, y equals x squared. What I'm going to do is I'm just going to take out that first half, which means what I'm restricting here is that y equals x squared, but only the values of x that are greater or equal to 0. Okay, and which is, I guess, if we're only graphing that part, then if we apply the horizontal test, it's only going to cut through that function at one point, because we've restricted the domain to only the positive values of x. Okay, now again, if we did the inverse of that, okay, so we knew from before that our inverse is y is equal to positive or negative the square root of x. But because we've only have half of the parabola and we've restricted for the positive values of x, then we will only need the positive values of the square root of x in the inverse. Okay, so the same rule applies for here. That means the inverse is going to look like that. Okay, and when we apply our vertical testing, we can see that it will only cut through the function at one point. Therefore, it's a function. Okay. So now what we've applied with the restrictions of the domain is that we've made the inverse a function upon those restrictions. Okay. So in this case here, the x values are also greater or equal to 0, and they are our domain restrictions. You could easily do exactly the same thing with doing the opposite. It doesn't mean you have to do positive values. You can do the negative values. So what we could do is we could change this around, and we could say that we want the values of x that are less or equal to 0. Okay, and therefore that will apply the same thing to the inverse. And instead of having the graph on the right hand side, we'll end up having the original to look like this. Yep. And then our inverse function is going to look like that. And both meet the same criteria. If you apply the horizontal test, it only hits it once. Vertical test, it only hits it once. Both are functions, which is what we want. So that's all I'm going to cover for today's session. A lot to take in, probably waffled a lot. So please let me know if you have any questions so I can provide some more clarity to each of these sections and maybe work through a few more examples. Okay, have a good day. I'll see you in the next video.